Excellent. And we are recording. So, hi everyone, we're back to some more plate tectonics today. And the first half of Lab 2 last week focused more on earthquakes, volcanoes, and different types of plate boundaries. Today's lab exercise is more heavily about an unusual type of volcanic activity that doesn't actually occur at plate boundaries themselves, but it's still actually affected by plate tectonics. And something that I find interesting is that they've actually very heavily used the movement of volcanoes related to hotspots to actually measure things like how fast plates move. So even though we think of hotspots as being volcanoes that are independent of plate tectonics still play a role. So the lab is going to be due next week, Monday, February 15th at 11:59 p.m. And one thing I want to mention is that it looks like everyone submitted the quiz or like the lab exercise part for Lab 2A, which we did last week. I noticed that not everyone submitted a file for the map of the plate boundary types and earthquakes and volcanoes. If you haven't done that already, get that uploaded and finished ASAP. I won't mark you late if you get that done before next week. If there's material from last week's plate tectonics lab that you have not yet finished, and you get it submitted before next Monday, before the 15th, then I won't mark you late. It'll automatically mark it as late in Canvas, but then I won't take points off. It's up to me to take points off. That's just Canvas sounding the alarm on that and being kind of obnoxious. Any questions about that? Yes, could you speak up a little bit? I can't hear you much.
Yeah. I just had a question. For every lab, there is a quiz, right?
Not every single one. Well, so for most of them, there's a combined quiz for parts 2 and A and B of the plate tectonics lab, and that's not going to be due next week. That's going to be due on the 22nd.
Okay, yeah, because I tried to see if there was like a quiz due for the lab of last week, but I wasn't able to have access to it. So
oh, no. You're totally fine. I didn't mean to scare you. There was a quiz on maps, which was the first lab we did that was technically due yesterday. And if you haven't done that already, go ahead and do that ASAP. If you get that done, if you get the maps quiz done today, I won't mark you late if anyone hasn't done that yet. But the only thing due next week, if you've already done the maps quiz, if you've already completed everything from last week, the only thing due next week is Lab 2B, including the file submission. And yeah, Jorge, I'm sorry it took you so long. This is challenges of online learning, but thank you all for being flexible. I appreciate that. Any other questions about anything I just said before I move on? Okay, so last class we focused on plate boundary types, and this is one of the slides from there, which actually does a really nice job of showing all three plate boundary types, as well as a hotspot. The only bummer is that it does show transform plate boundaries. It doesn't show how sometimes they can become really elongated like they do with the San Andreas Fault, but it's fine. So we have divergent boundaries, and divergent boundaries, how many examples of divergent boundaries are there on this diagram actually?
I just see one.
There's actually two. There's one out here in the ocean, and then if you look over here to the right, there's the continental rift zone, which is marked as a young divergent plate boundary. And that's actually kind of meant to show you that divergent boundaries, actually, we think of them as being ridges out in the ocean, but they usually start on land. The funny thing is that the magma upwelling here, it's producing oceanic crust without an ocean. The ocean ends up covering oceanic crust because oceanic crust is so dense and because it sinks down more. It's not because the ocean is there. The ocean comes there because the rock is there, which is kind of funny to me. But divergent plate boundaries are where you have on land. Actually, Death Valley is a really good example of a rift zone that did not fully turn into an ocean. The rifting stopped, and so now we have Death Valley dropped way down, and we have oceanic crust. We have basically ocean floor crust on the floor of Death Valley, but it didn't get all the way to opening wide enough for an ocean to fill in. But that's why Death Valley is below sea level, because it was really a young ocean forming. And that's kind of what this is trying to show here. But when the ocean does fill in, you get an ocean spreading ridge. And that's where new oceanic crust is produced and heads to either side of the spreading center. And I do see a question about the moho and the crust. The moho is not something you need to worry about, but it's the boundary between the mantle and the crust. The mantle and the crust, remember, are two chemical layers of Earth. I didn't really linger on the difference between how you can define layers of the Earth in terms of their chemistry versus how you can define them in terms of their physics. I mentioned how with plate tectonics, we care about the fact that the crust, actually the moho does kind of show something here. You see how the crust is kind of attached to this gray stuff. So the moho shows that there is a boundary between crust material, which is chemically different from mantle material, but that the uppermost part of the mantle is still part of the lithosphere. It still moves with the crust because it's a rigid solid. So the moho is showing where within the lithosphere you transition from crust to what you'd call lithospheric mantle. And then down here is actually the boundary, the boundary between the gray material and the orange material is actually where you have the boundary between lithospheric mantle and asthenospheric mantle. And remember that the lithosphere is the part of the Earth that makes up the plates themselves, the rigid part, and the asthenosphere is the plasticky solid that those plates kind of float over. Does that make sense? And does anyone have questions about that? Because that's an excellent point. Okay, cool. But that's kind of a brief recap of how the layers of the Earth fit into all of this. Anyhow, I finished up with divergent plate boundaries. So you have plates heading in opposite directions. Convergent plate boundaries happen when two plates have a head-on collision, basically, and either one of them subducts, which you can see happening in two separate places here. One where you have a plate with ocean crust subducting under a plate with continental crust. And something I want you to notice here, on this volcanic arc, I briefly alluded to this last time, but is there just one volcano that has smoke and magma, or are there volcanoes all up and down this arc that have smoke and magma?
All up and down the arc.
Yep, you can see there's smoke further off, and that's meant to show that this trench also extends into the background, into the far off. You can see because this trench shows you that subduction is happening all along the front of this volcanic arc. It doesn't show it on this diagram, unfortunately, but if two continents come together, then you get collision and mountain building like you have with the Himalaya presently. And then transform boundaries are found at the mid-ocean ridges, where the stagger of the divergent segments, the ridge segments where the magma is actually coming up, those are staggered, and that creates plate boundaries that are perpendicular to the ridge spreading center themselves. And the crust moves horizontally in opposite directions, but it doesn't move up or down, and there's no volcanism, nor is there any crust recycling like you have at subduction zones. And most transform boundaries are really small in just these tiny connector segments, but occasionally they can get warped into much longer plate boundaries, like the San Andreas Fault, close to where most of y'all live. Close to where I live too, but I'm more surrounded by the various subsidiary faults, but I can talk more about that another time. But anyhow, the thing with this diagram is that most of the volcanoes are associated with plate boundaries. Now, what about the hotspot? Does that appear to be at a plate boundary? Does it appear like two plates are either going in opposite directions or coming together, or that there's side-to-side motion? I heard something.
I think it is on a plate boundary.
Why do you think so?
Because the hotspot is kind of located between the lithosphere and asthenosphere.
So that's a good point. You see, I think what you're pointing out is that you have this magma upwelling occurring around the boundary of the asthenosphere and the lithosphere. Yeah. So you'll notice that the other places where volcanism is, you see how the plates kind of get pinched here, and the magma is coming up between the plates, like on this tiny little conduit. And that's kind of happening here also. Like oops, I'm so sorry. You can see that these are distinctly different plates here. One is made of continental crust, one's made of oceanic crust. Here, what's happening is that the magma from this hotspot is actually simply rising through the plate and not really being affected by it. It's being dragged a little bit, but essentially there's a conduit of magma rising through the plate. So one thing I want to ask you is that with this volcano, there's a number of other nearby volcanoes. What do you notice about them compared to their size? What do you notice about them with their size compared to this one, as well as with whether they appear to have any smoke coming out of them?
This one has a little bit of smoke coming out, and it's more rounded like a hill instead of being more like the steep volcano like structure that we're used to.
Yep. Yep, precisely. Hotspot volcanoes do tend to be more rounded because you get a really large volume of magma forming, actually. Specifically, though, I was actually referring to not this volcano versus the subduction volcanoes, although that's an excellent point. I was referring to this volcano here versus the other little islands next to the hotspot. Like, are these other islands as big, and do they have smoke coming out of them?
No, they're
No.
tiny.
No, they don't. And that's how you can tell that this is not a subduction zone and not a plate boundary. Because if there were a plate boundary, you'd see a chain of volcanoes. And that's true at mid-ocean ridges also. You have basically a chain of fissures going all up and down this plate boundary. But you just have one spot where magma's coming out here. This isn't a plate boundary. This is actually, these smaller islands actually are, show you that this area within this plate used to be over the hotspot. So for the plate between this ocean spreading center and this trench, what direction is it moving? Is it moving to the left of the diagram or to the right? You can kind of extract that based on which direction the ocean is spreading and what direction subduction is going. What direction is the plate that the shield volcano on moving? Is it moving to the left or to the right?
To the left?
Yes, it's moving to the left because it's subducting over here. And you can actually see how the plate movement has what the plate movement has actually done is it's dragged the volcanoes that used to be over this hotspot over in this direction, over kind of to the left and behind. And what that means is that these volcanoes aren't active anymore. They become extinct volcanoes as they're pulled away from the hotspot. Why do they get smaller? That's something I'll go over a little bit. But essentially what's happening is that the largest island is where the hotspot is presently. That's where the active volcano is, and the actual eruptions of the volcano are what's building the island. But then as the plate drags these volcanoes farther away from the hotspot, they no longer are active, and you get this chain of dead volcanoes that are slowly being eroded by the ocean. And that's the pattern you see in the Hawaiian Islands. So that's what we'll kind of be working on today. Hotspots are going to be the main focus of today's exercise. Before I move on to the next slide, does anyone have questions about anything I've brought up so far? Yes, precisely. Jorge had a question in chat about it getting smaller because there's no more magma. And yes, because there's no more magma erupting as lava and cooling to form rock. Because islands like Hawaii, which are formed by hotspots, those islands exist above water because enough magma solidifies to become rock. And where the volcano is active, that's happening constantly. New eruptions are adding more lava flows, aka more land. But then when the islands get pushed out away from the hotspot, there's no more magma feeding them, and they just get eroded and broken down by the waves. So yes, excellent point. So I briefly showed you this slide before, but hotspots are one of the few examples of a geologic process that's not directly linked to plate tectonics. But one thing that's interesting is that there is a hypothesis that when spreading centers develop, like when Death Valley just started to rift apart, that was related to a hotspot. So it does seem that hotspots can sometimes evolve into plate boundaries, but we're not really going to be concerned with that much for this class because that's a broad geophysics question that even geophysicists don't have a good handle on just yet. Now, but anyway, some hotspots just stay hotspots, like the Hawaiian hotspot. And the best model for it is that there's a plume of molten material rising from deep within the mantle. And there's a huge amount of hot material rising. It's rising because it's hot and buoyant. And something you'll notice with this diagram is that when a hotspot first emerges, it just floods everywhere. Lava flows out everywhere, and there's gigantic lava flows. And that actually shows up in the Yellowstone Hot Spot. Anybody know about the Columbia River basalts in Oregon and Washington? Anybody seen those ever? if you ever get a chance to drive over a lot of kind of where the Columbia River is on the boundary of the states or in Eastern Oregon, there's just lava flows that have covered everything. And that's actually related to the Yellowstone Hot Spot. It's from this initial stage. When that kind of dies down, the hot spot will start bubbling up at a more normal rate and it'll produce a volcano. That volcano will get dragged away by the movement of the plate. You can see that in this example is showing that the plate is moving to the left on this screen, and that drags the flood basalts away from the hotspot and then drags this chain of volcanoes away from the hotspots. And the idea is that the hotspot is kind of just bubbling up magma just constantly, and the plate is moving constantly. So the chain of volcanoes happens as a result of that. And it's not quite as simple as that. Hotspot movement does get affected. The hotspot does get affected by plate movement a little more than we're going to really delve into in this lab, but you get the idea. And the reason they're called hotspots is actually because the mantle plume is literally just hot enough to melt. Something interesting about the volcanism that you get at divergent and convergent plate boundaries is that at divergent plate boundaries, you get melting because the pressure drops. And at convergent plate boundaries, subduction zones, you get melting because the downgoing plate brings fluid into the mantle, and that actually allows the mantle to melt. But hotspots are just really hot, actually, so they're aptly named. And the Hawaiian Islands are probably the most famous example of them. The Hawaiian Islands are only the youngest of what's known as the Hawaiian Emperor Seamount, the Hawaiian Emperor Seamount chain, which actually stretches all the way from the Big Island of Hawaii to the rest of the Hawaiian Islands, and then onto what are known as the Northwestern Hawaiian Islands, which are the remnants of old volcanoes, and they're tiny uninhabited islands that have been broken down. Those volcanoes were active millions of years ago. And then there is not a chain of islands poking above water here, but there is a chain of extinct underwater volcanoes known as seamounts that actually extends all the way up to the area off the Kamchatka Peninsula and off the coast of Alaska. It's a little bit hard to see in this diagram, but there's kind of a darkened feature here in front of the Aleutian Islands, and the Aleutian Islands are a chain of volcanoes. If you've been lucky enough to go to the Aleutian Islands off the coast of Alaska are a chain of volcanoes where you actually have active volcanoes running up and all down it. So what's this black thing then? What's going on here? If you have volcanoes behind it.
And a plate?
That's a plate boundary. There's the Pacific plate, and then there's this plate here. And actually that so the boundary between those plates is the darkened feature I'm pointing out, and that's a trench. That's where subduction's happening. So the oldest volcanoes in the Hawaiian Emperor Seamount chain are actually being subducted near the Aleutian Islands in Russia. So they go a long way. It's one of the longest and most continuous hotspot chains in the world. And fittingly, not all of the Hawaiian Islands have active volcanoes. There's active volcanoes on the Big Island of Hawaii, which is biggest because it's being built by active eruptions. And then there's a dormant one on Maui. Haleakala, which there's a national park there, erupted within human lifetimes. And it's still, if you're wondering why there's multiple volcanoes erupting, hotspot geometry is kind of complicated. And I'm actually going to show a video animation at the end of this spiel that might give you a sense of that. But Maui is still kind of sort of close to the hotspot, and Haleakala still has eruptions. But then there's a ton of inactive volcanoes on all of the islands. These islands exist in the first place because the hotspot was erupting, because there was enough lava being produced for them to poke out above the water. The island of Hawaii, the mountains on the island of Hawaii actually go all the way to the seafloor. And that's why you may sometimes hear that Mauna Kea, if you consider the height from the base to the peak, it's technically higher than Mount Everest. Mount Everest is just higher over sea level because it's not an underwater volcano. But that's where that statistic comes from, if you've come across that before. But the volcanoes on the older islands, like where Oahu, where Honolulu is, have not experienced eruptions in ages. And that's one reason why so many people live on Oahu, because there's no volcanic activity to burn things down. And you notice the islands get smaller to the west. They get smaller because erosion from waves and wind is breaking them down, and they're not being fed by eruptions anymore, because volcanic eruptions are literally what build the land. the mountain wasn't there before the volcanoes happened. The volcanoes happened and built up the mountains over time, which is something I kind of had to learn as a geologist, and that's a really good mindset to get into. Mountains exist as a mountains don't make geologic processes, they exist because of geologic processes. Now, if you go northwest of Niihau, and Niihau is the most western inhabited island. It's the island that is inhabited by a small village of native Hawaiians, and you have to get permission to go there because it's technically privately owned by some Scottish guy. I don't really know how that happened, aside from colonialism, but there you go. But anyway, that's the last inhabited island. And then if you go to the northwest, you get to the tiny islands that are little more than battered remnants now. Little scraps of volcanic rock, but mostly the volcanic stuff is sunk, and you have these little coral reefs growing around them, and that's what makes the islands. And then if you go farther north, you simply get to a bunch of seamounts, to mountains that don't poke above the water anymore because their tops have been eroded down by the waves. And then they disappear into the trench off the Aleutian Islands eventually. But that is the pretty astounding example of the Hawaiian hotspot chain. There's also a hotspot in Iceland, and Iceland actually lies over the Mid-Atlantic Ridge, and the Mid-Atlantic Ridge doesn't actually produce that much magma, all things considered. And remember that during seafloor spreading, the magma is kind of continuously being pulled to the sides, so it doesn't build a high volcano. But in Iceland, we have a really weird example of a hotspot happening to erupt right underneath the Mid-Atlantic Ridge. And so the combined volume of the mid-ocean ridge magmas and the hotspot magmas produced enough lava for an island, a really large island, to form above the surface. So Iceland is one of the world's largest volcanic islands, and it exists because this gigantic hotspot is erupting and adding to all of the magmas from the mid-ocean ridge. And this picture in the upper right is actually one I took. This is where you can walk through the mid-ocean ridge on land, because the mid-ocean ridge gets kind of shoved up onto land, and you can walk right through where it is. It's moved a couple times actually, but the mid-ocean ridge actually goes on land through Iceland, which is pretty cool. But you don't need to worry about what all these different terms mean, but they refer to different categories of lavas based on their chemistry. And it turns out that the lavas that you form at mid-ocean ridges have different chemistry from those at hotspots and from those that you erupt at subduction zones. And they've found a really interesting mix of volcanoes that look like they're just erupting hotspot magmas, and volcanoes that look like they're related to the mid-ocean ridge, and then some that show a mixture. So Iceland is a big volcanology research hotspot. And that's why I went there. I was doing a volcanology project. And then a bit closer to home, there's Yellowstone, which is one of the very few examples of a hotspot on land. And what's one reason why you might not expect to see as many hotspots erupting through continental crust? What's different about continental crust versus oceanic crust?
It's thicker.
It's thicker, precisely. That's one reason why most hotspots seem to erupt through ocean crust. But the Yellowstone hotspot was actually voluminous enough to break through continental crust. And this diagram in the upper right, the light green color shows they actually cover more than this. Like some of the Columbia basalts, you can find them along the Oregon coast, but these basalts, this entire area covered by the light green, that is all from when the Yellowstone hotspot first showed up and erupted just tons and tons of magma. That magma ended up forming what's called a flood basalt, when the lava just goes over everything and covers everything. And you can still see that if you drive through Eastern Oregon today. Last summer, I was working in an area where you could see that. Apparently, this is actually considered a relatively tiny example of a flood basalt. There's much bigger ones from longer ago that you can find in Russia and in India. But in any case, the hotspot, so the eruptions occurred from this area, and then the hotspot ended up down here and has, the hotspot hasn't really moved much, but the plate caused a hotspot that was originally erupting under Oregon and Washington. Now that hotspot is under Wyoming, under northwestern Wyoming, where Yellowstone is. And they've found a chain of volcanoes that chemically and geometrically can be linked to this hotspot and to the plate movement of the North American plate over it. Yellowstone is a caldera. That's where you have a leftover volcanic crater where a really big eruption emptied out the magma chamber and caused the volcanic cone to collapse. And so it's rebuilding presently. And everyone loves to talk about the Yellowstone supervolcano and how dangerous that might be. And it's possible you could get a large eruption, but honestly, right now the magma chamber is refilling and it's going to take a while for it to rebuild, people think, but people are working on that. But if anyone's ever wondered why there's so much in the way of hot springs and geysers, it's from heating from the magma below, from the Yellowstone Hot Spot. And one thing that's interesting actually is that the Yellowstone Hot Spot, the fact that it goes through continental crust is why it ends up being so explosive. The Hawaiian volcanoes don't really explode very much. Sometimes they do, but they're more known for wider lava flows. The Yellowstone volcano is known to have had some extremely giant explosive Mount St. Helens type eruptions. And actually, does anyone know about Crater Lake in Oregon? Has anyone been there? If you ever get the chance to visit Crater Lake National Park in Oregon, it's actually another example of oh, that is my cat stepping on the keyboard, but she put it back. But that's another example of a big volcanic eruption just emptying out at once. That's not from a hot spot, but it's from a big explosive eruption. And it's explosive because the magma coming from the hot spot actually mixes with the granite in the surrounding continental crust, and it becomes lighter colored, which is something we'll talk more about when we do igneous rocks. But lighter colored igneous rocks are going to have more silica in them, and the silica makes the magma stickier, and the stickiness traps gas, and that's actually what causes them to be so explosive. So anybody have questions about hotspots or any of the hotspot examples I've brought up?
How long will it take for the magma to fill up in the Yellowstone?
I don't know. I've seen estimates and I don't remember, so I don't want to give you a bad number, but but if you remind me, I'll look that up. I'll do my best to remember that, but if you email me, I'll look that up also.
Thank you.
Yeah. Okay, so today's lab is all about hotspots. So today's part of the lab has a short lab, or it's not even really a short lab like assignment where you have a couple of multiple choice questions on where you find the youngest volcanoes in the Hawaiian Islands or where you find the oldest volcanoes in the Hawaiian Islands. And before I end this presentation, I'll open up Canvas and kind of show you what I'm talking about. There's a small number of questions about calculating the rate of plate motion, but the big part of the lab is that you're going to be making a graph that shows how the ages of the different islands, aka the different volcanoes in the Hawaiian chain, correspond to their distance from the hotspot. And then you'll use some of those numbers to calculate a rate for how fast the plate is moving. So it's shorter than last week, and it's due next Monday, February 15th, and again at 11:59 p.m. And again, if you have not completed anything from Lab 2A, then please get that done before then. Also, I won't mark it late. And the graph is what you're going to be uploading, and I will actually also have a short video on this, but for your chart, what you're going to be doing is plotting two types of data that each go with a particular volcano and putting those on a two-dimensional graph. So the data that you're interested in are the age of the particular volcano and then the distance of that same volcano from the hotspot. So there's two tutorials linked in Canvas, and I'm going to play one of them once I stop the recording, actually, for those of you who want that. But what you're first going to want to do is draw axes. You're going to want to draw a vertical and a horizontal axis. And this is an example. This is not what yours is going to look like exactly, obviously, because it's not measuring volcanoes. But it does do a nice example. It does do a nice job of showing how you want to label what data is being shown on your horizontal axis and what units you're using. And then what data is being shown on the vertical axis and what units you're using. Because each point has two bits of data associated with it. This particular circle here is associated with 4 centimeters diameter, and then 2.7-ish height. And you can see how you can figure that out by tracing to the axis. And this is why the axis needs to have number labels, actually. So for the graph that you're going to be making, the x-axis, the horizontal axis, is going to be the age of each volcano in millions of years or mega onum, MA. And that's a good abbreviation to memorize if you haven't already, because that's going to come up a lot. But MA means millions of years. And then the y-axis, the vertical axis, is going to be the distance from the hotspot in kilometers. And one thing you want to do when making your graph is that you want to look at you want to first compile all of your data. You're going to look at the ages are given in a chart on Canvas. And then part of the exercise is you using a map on Canvas or Google Earth or Google Maps to measure the distance of each island from the big island, which is we're treating as that's just where the hotspot is now. And you want to figure out, in your case, what the oldest number that you have to plot, what the oldest age you have to plot is, because that'll determine how long the x-axis has to be, and then what the longest distance from the hotspot is, because that will determine how big the y-axis has to be. And so, for example, if the biggest age were 95 million years, it's not. That's me throwing it out, but you would a good number to set the x-axis to would be 100 million years, so that it encompassed anything that was smaller than that. And then you can subdivide the plot into 10s or 20s or whatever makes it easier for you to be able to pretty accurately put where the rest of the points are. I'm not going to be grading this on exactly where everything is, but the shape, because you're going to get different measurements, because it's, again, even if I say measure from the center of the big island, everyone's going to do that slightly differently, but the pattern should be about the same for different people's charts. And as you go about this, I'm happy to take a look at your charts to give you a sense of if you're doing it correctly. What I often find easiest is to figure out the x-coordinate first, and the x-coordinates are the ages, and you're given the ages in a chart on Canvas in the exercise. What you can then do, if you're drawing on graph paper, you can use a ruler or straight edge to go straight up until you find the y-coordinate that goes with that, aka the distance. You have the age for one particular island, and then you're looking for the distance from the hotspot for that same particular island. And the table on Canvas provides some structure for you to get this organized if you want, or you can copy the data into Excel. Before I jump over to Canvas to show you what's in the lab, does anybody have any questions? And I will be, once I shut the recording off, I will be also playing one of those tutorials for those who want it. Okay, cool. So I'm gonna jump out of PowerPoint and go back over to Canvas. So this is now on a preview. This is now on a preview of the quiz of the lab. Excuse me. It's Canvas uses the term quiz for everything, which I find confusing. But ignore this. It's going to be due to that's due 1 week after the lab is due, so don't worry about that right now. But you actually have some good resources in here. There's the plate boundaries map if you need to refer to that, and then there's a good textbook chapter on hotspots here. This is from the online textbook, and you should be able to log in here and just pull this up if you want to read over another person's take on what's going on with hotspots. They also have some good information on the Yellowstone Hot Spot. And actually, the most recent eruption of the Yellowstone Hot Spot occurred 631,000 years ago. Should the hot spot erupt again? Blah, blah, blah. This doesn't tell me anything about when it'll erupt. Okay, I'll see if I can look that up because I'm curious. Honestly, with the Yellowstone Hot Spot, there's so much misinformation out there, and there's so much fear mongering. But anyway, and then so there's some more information here, kind of giving you another diagram of hotspots. And this is the map I was talking about that you can use to measure distance. So this has the main Hawaiian Islands, and the hotspot is under Hawaii, the big island right now. And so that's why in this chart, where it says distance from hotspot for Hawaii, it's 0, because that's where the hotspot is right now. So there's a couple ways you can do this. All of these islands are labeled, and it might be easiest to do in here because you have to tweak around with Google Earth sometimes to get it to show all of the names of these tiny islands because nobody lives on them. But you can use this scale to approximate how far each of the other islands are from from the main island, or you can use Google Earth or Google Maps to do this. And I don't particularly care what you use. I realize everyone's going to get slightly different numbers. You can either do this on physical graph paper, or you can improvise with line paper if you're comfortable doing that. There is also you can use Microsoft Excel to do this, or Google Docs. I also added, there's a PDF of graph paper if you just want to download it and draw on that. You can also find that under lab resources, but this link should take you right there. And this is the chart I was talking about. You're not going to pick every single island, but for all of the islands in this chart here, you're going to figure out how far each one is from the hotspot in kilometers, and then you're going to plot age in millions of years versus kilometers. And you can see they're younger than 90 million years. That was an extreme example. But Midway is the oldest volcano that we have here. So Midway should give you an idea of what maximum you want to put on your graph. Like what's the biggest age and what's the biggest distance you're going to have to plot. And this upload window linked here is where you're going to actually upload this. As for the lab questions, there is one calculation you have to do. Notice it says using the values you obtained for Midway only. So once you're done with this, once you've made your plot, you'll have a distance, you'll have a number, you'll have a distance for Midway, and you'll have an age for Midway that's already given. So you're going to use the amount that the hotspot has traveled from Midway to the modern location over the Big Island, as well as how long it's been since the Midway volcano erupted, to calculate a plate motion rate. And then there's a question about comparing that to what the actual rate is. And if your number is really different from that, that's okay. We're doing a really simplified version of this, and plate movement and hotspots are difficult, and even geophysicists do this about it. So, and then these are just a couple other questions about where the youngest rocks are. And before you do question 5, Google Loihi, because Loihi is pretty cool. The hotspot is dynamic, and it's interesting to think about how the Big Island is going to cease to exist also at some point, how it's going to be supplanted by younger volcanism. And I think that's everything in here I wanted to show. I did want to mention that I don't know why I had such a hard time finding this last time, but the lecture PDFs for the lecture, at least from the last time Dr. Bird taught this, they are here in files. If you need to get your hands on old lecture material. I don't know why I had such a hard time finding that last time. But that's about all I have before I switch over to the videos, and I'm just going to stop recording when I play the videos because YouTube doesn't like that. But does anybody have questions about the quiz or any of this stuff? And don't get overwhelmed by this. A lot of this is just here as extra resources, or if you want another take on hotspots. But it's not a lot of new information. Okay, I'm going to stop the recording. And people are obviously welcome to work on the lab, but I'm going to play a couple videos for those of you who want to watch those first.